Hello students, welcome back to yet another session in this unit, Vortex tube refrigeration system. We have one more topic to cover in this unit, so that we are going to discuss in next session. And these are the topics in this unit. We have vapor absorption system, adsorption system, so steam jet refrigeration system, thermoelectric refrigeration system, air refrigeration system, magnetic refrigeration system. Now we are going to discuss vortex tube refrigeration system. So in next session we are going to see pulse tube refrigeration system. So what vortex tube refrigeration system? It is again an unconventional process, unconventional refrigeration system, and it is not a regular type of system. So construction and working. The vortex tube is a simple device for producing cold and was invented by Rank and further developed by Hilsch. The vortex tube, which shows a good promise to is due to Palmker and is called short vortex tube. So here this is the diagram, and you can see the cold. This is the cold side. Inside you can see this is the vortex tube, and we have nozzle. Nozzle is here, and this is the throttling valve, and this is warm side and this is colder side, and now we have a diaphragm. So from this diaphragm, this diaphragm separates both cold side as well as warm side, and this is the throttling valve, and we can adjust this using this arrangement. So this is a simple construction and very simple type of device, and we have three parts. One is throttling part, and one is warm side, another side is cold side, and that is separated by nozzle and diaphragm. So vortex tube refrigeration system, the figure shows cross section of 16 vortex tube of type experimented by Timothy and Hinch. It consists of the following parts. So the first one is nozzle, and we have diaphragm, cold air side, hot air side, throttling valve. So air at room temperature and about 5 bar is passed through the nozzle, which is located between warm and cold ends. So here nozzle and diaphragm both are kept between the cold and hot sides. So after expansion through the nozzle, so that is air from tangentially into the vortex chamber. So this is the simple expansion nozzle, and expansion through nozzle it happens, and that is happening through tangentially into the vortex chamber. So vortex tube refrigeration system, the diaphragm forces the vortex to deviate towards the warm side. So here the vortex form is very important, and the tube is formed, or tube is made in vortex form. When the valve is adjusted, letting only a fraction of air leaving the warm side, it is found that two streams of air emerge. So that is one at the warm end and another is at the cold end. So the warm side temperature is higher than that of air at inlet, and the cold side temperature is lower. So cold side temperature is obviously lower, and by controlling the opening of valve, the quantity of cold air and its temperature can be varied. So advantages here, there is no leakage problem as it uses only air as refrigerant. So here also there is no chemicals used as refrigerants, and air itself is the refrigerant. It is simple in design and needs only control of valves for appropriate functioning. No moving parts, light in weight, requires less space. Initial cost is low. At places where compressed air is readily available, its cost is also lower. No expertise attendance is required. So here to operate this, and the skilled people are not required. Anybody can operate this. So Vortex tube refrigeration systems disadvantages: low COP. So that is the biggest disadvantage. COP is very lesser, and limited capacity. So it can cool very with limited capacity only. You cannot employ it for bigger space. So Vortex tube refrigeration system applications. The Vortex tube finds use in the following fields, that is air suits, aviation, cooling of gas turbine rotor blades, spark cooling, cutting tools, shrink fitting, laboratory sample cooler, heating and cooling requirements simultaneously. So cooling enclosures. So these are the few applications, and apart from this we have few more applications also. So here air suits, aviation, cooling of gas turbine rotor blades, spark cooling, cutting tools, shrink fitting, laboratory sample cooler, and we have heating and cooling requirements simultaneously, cooling enclosures. So here these are the few applications of vortex tube. Apart from this, we have other applications also. So coefficient of performance of vortex tube. The COP of the vortex tube is defined as the ratio of cooling effect to the work input to the air compressor. So here air compressor is also employed. The expression of COP of the vortex tube is given as the COP is equal to isentropic efficiency and compression efficiency Pa by Pi to the power gamma minus 1 divided by gamma with perfect heat exchange. So with perfect heat exchange, this is the COP equation, and where so vortex tube isentropic efficiency is isentropic efficiency. So isentropic efficiency can be computed like this. So isentropic efficiency is equal to actual cooling divided by ideal cooling. Actual cooling divided by ideal cooling. So N comp, that is the efficiency comp, is equal to eta comp equal to compressor efficiency, and Pi is the pressure of air at inlet to the nozzle, and Pa is the ambient pressure. If isothermal compression is considered, then the COP isothermal equal to gamma divided by gamma minus 1 into isentropic efficiency into compression efficiency into 1 minus Pa by Pi gamma minus 1 divided by gamma into natural logarithmic of Pi by Pa. So this is the governing equation, and the general expression for COP is modified like this. So this is COP equal to MC into CP into delta TC divided by MI into CP divided by the compressor efficiency into PI by PA gamma minus 1 divided by gamma minus 1. So this is the expression for COP, where I and C stand for inlet to nozzle and cold end respectively. So inlet to nozzle. So Mi is the inlet to nozzle. So here, and you we have MC is the cold end, and mass at Mi and MC. So delta C can be calculated like this: Ti minus Tc. So observations on COP of Vortex tube. So that is, it has been observed that the efficiency of compression is always considerably small. Therefore, COP of the Vortex tube will also be very small, of the order 0.15 to zero point 0.2 only. So COP is very small here, and this is another disadvantage. With this, we cannot employ to our industrial or domestic purposes. So that's why it is not much popular under normal operating conditions. To obtain high COP, the pressure ratio should be small, which will give very low refrigeration capacity. Hence, it is not applicable to large capacity plants. So these are the observations of COP of Vortex tube. So this is the Vortex tube refrigeration system all about, and we have one more topic left out that we will see in next session, students. So there ends Vortex tube, and we will be completing this unit in next session itself. So these are the references. You can refer the Rajput or Kurmi. Kurmi is a very good book. You can rely on this. And Rajput is also very good book. CP Arora is also good book, and but it is little vast and little bigger in bulky in size. Either you can refer that, or Rajput you can refer. And my preference is Kurmi. It gives a very simple way. Everything is given in a very simple way. You can refer Kurmi book or Rajput. Both are good, and we have other references also, students. And with this, we stop here. We will meet again in next session, where we are going to see the pulse tube type of refrigeration system, and that is also very similar to Vortex tube only. And we will discuss in detail about pulse tube refrigeration system in next session. Thank you, students. We stop here. We will meet again in next session. And one more topic, that is the only topic left out in this unit. We will be completing that. So we stop here. Thank you. Thank you, students.